Okay, our new topic, probability. Everybody probably has used the language of probability, and you normally use it to describe how likely something is. No, so you might say like, oh God, it's pretty likely that it's going to rain tomorrow. Or it's very unlikely that politician is ever going to tell the truth, which is my opinion, virtually all of them. Or you might say that it's just as likely as not that I'll get my homework finished tonight. Now, when you use those kind of vague terms, you're really using the language of probability. Probability is just a number that we attach to how likely something is. And what we're going to do is we're going to look at how we can actually calculate those numbers, because they're very often very useful. Probabilities get used in gambling. That's why casinos don't go bankrupt. But they also get used in risk analysis. Insurance companies need to know how likely it is that you're going to die in, the next 50 years or whatever, and they adjust their insurance premiums accordingly. So
do they use this?
Say again?
Do they use that same like theory for like colors of cars? Because I heard that when you have a red car, your insurance is higher. And I do have a red car, and it is pretty expensive, but I've heard that. I don't know why. The color of the car.
If they did that, it would be the second one. It would be using what's called empirical probability. So it could well be the case. Now, the reason they do that might not be directly because the car is red, but red cars may be getting accidents twice as often as blue cars do. So if you've got a red car, they're going to double your insurance premium to cover the risk. And I'm making those numbers up. It probably won't be anything like double, but it might be 10% more likely of an accident. So your premiums follow that. And that's called an empirical one. So yeah, they use them in insurance all the time. A house that is in a really bad part of town that's had mostly peaceful riots in the last year is probably going to have very high insurance premiums, because evidently mostly peaceful riots aren't that peaceful. So that would be an example of insurance companies. So you can use it in other ways. So let's start off with, what kind of numbers do you get? Probabilities are in the range of 0 to 1. Now, at the 0 end, you're talking about an event that will not happen. It will never happen. That's what a probability of 0 means. A probability event being 1 means it will happen. There is no ifs and buts. It's going to happen. It's hard for me to do zeros and ones, but I'll pretend I know what I'm talking about here. The probability that the President of America is going to tell the truth every single time for the next year is 0. That ain't going to happen. He's going to tell a lie sometimes, even if he doesn't know he's lying, which I doubt. Probability of 1, something that's guaranteed to happen. How about the probability that I tell a good joke today? Now, I can put a probability of 1 on that because I am arrogant enough to think my jokes are good. You, on the other hand, might put it over at 0. You may, of course, kind of cover your bets. So if the probability that I'm going to tell a good joke today is kind of, yeah, it's just as likely to be true as not, right? That's what a 0.5 would be. So that would be just as likely to happen as not. And The further you go towards the 1, is it not the more likely this event is going to happen? And the closer you get to 0, is it not the less likely it's going to happen? So for instance, if I was just randomly picking events, do you know getting hit by lightning is probably about there? Would you agree? And the chances it's going to rain in Washington in the next 14 days is probably going to be up there, right? And some events are kind of close to the middle, and some are over here and some are over here. So we need to kind of look at how that's kind of the spectrum of probabilities. And when they're written as decimal, this is the scale, but they aren't always written as decimals. Probabilities can also be written as percentages. Would you agree that's essentially that's a same match, isn't it? A 0% means it ain't going to happen. A probability of 100% is it's going to happen, and a 50% probability is just, you know, just as likely as not to happen. And then there is a third way in which probabilities can be written. They can sometimes be written as fractions. So when you go through your homework, pay attention to what they want, because you know how fussy WebAssign is. So if they say, give me a probability as a fraction, then call it a half. If they say, give me as a decimal, call it 0.5. And if they say, give me as a percentage, call it 50%. Because if you put in a half and it wanted a percentage, it's just going to tell you you're wrong. There are 3 major types of probabilities and how they're calculated. The first one is personal probability, and that totally lacks accuracy. I, for instance, did a personal probability when I went and said, the probability I'm going to tell a good joke today is 1. Wasn't that just a value judgment by me? Right, so if I went and said to you, who we pick? We'll pick Griselda. Griselda, you're in the hot seat. Can you hear me? Yeah, okay. Your own personal opinion. What's the probability that it's going to rain tomorrow? Give me a percentage. What do you think that it's going to rain tomorrow?
80%.
80%. So what Griselda's telling me is that it's more likely to rain tomorrow than it's not. Now that 8% is kind of gut feeling, right? Do you know if you put a number on something to try and emphasize how likely it is, and that's really just a personal one. Isn't there no real way that you could easily test those probabilities? So their biggest problem is that they lack accuracy. So we tend to keep away from them, because couldn't my idea of what the answer is be different from David's? Empirical probability. Used a lot. Get example of that. Suppose you have a factory and it produces 250 cars a day. And at the end, they're always checked to see if they're good to go, right? Or at least a good company would do that. 15 have some problem. What's the probability that in this factory, a car is going to have a problem? So if a car comes off the assembly line, what's the probability or the chance it's going to have a problem? Well, in this case, 15 out of 250. And if I do that as a decimal, it's about 0.06. If I want it as a percentage, it would be 6%. And if I wanted it as a fraction, it would be 3/50. Would you want to buy a car from this company?
Well, I'd want to know what other companies
Oh, that's a
probability.
good question. I never thought of that. Yeah, so if the other companies are 12% and 15%, isn't this company actually doing a good job of reducing the problems? You don't want to buy a car if you're likely, but get it, and then there's a great chance that something's wrong with it, and you have to send it back into the dealer to get it fixed. And yeah, we don't like that. Empirical probabilities then are good at calculating probabilities. Probabilities are calculated by a fraction. You put on the top the number of ways something can happen. In this case, there were 15 of them that had a problem. And the bottom, the total of numbers that could happen. All 250 could have a problem. That'd be a weird thing, but it could. And that's where that came from. Suppose I wasn't going to do a test on every single item, right? Suppose I've got a company and they make cornflakes, right? Put them into a box, next one. And they do, lots and lots of them. It'd be very impractical, wouldn't it, to open all the boxes of cornflakes and check that the cornflakes inside were okay, right? There wasn't moldy or there wasn't a weight problem. Because wouldn't you, well, I mean, that would just double, treble your cost. They don't do that. So how do they keep track of it? Well, you can imagine that they might take a little sample. And they took a sample, they say 10, and one was bad for some reason, right? Then in this case, the probability that you get a box of cornflakes and it would be bad would be 0.1. Now, that's just a sample, right? Let's say that they make 50,000 cornflakes a day, right? But you only test 10 of them and one are bad. That is called an empirical probability. It's calculated basically just on numbers, right? You've got some numbers. That's a very small sample. If I went and picked another 10 from that company, isn't there a good chance that maybe the next batch of 10, none of them were bad? And then another batch of 10, I might get 3 bad. Can you see it could jump all over the place? Because when you only pick 10, isn't it very easy to get a different answer, even, for something like that? Now, on the other hand, if you tested 1,000 of them, wouldn't that give you a more accurate answer of how good, the quality of your product, right? If I did 1,000 of them and I only got 2 that had a problem, then the probability in this case of getting one that's no good is what, 0.2%? So the problem with empirical probability is that they do give answers to what is the likelihood of something being bad, or if we're going that story, but you need big samples to be accurate. Suppose I was interested in the number of people who have COVID right now. And all I did was I got 10 people and I tested them. And one had COVID. If I did that, I would be telling you that 10% of people in Bremerton have COVID, even if they don't know it, right? Because some of you catch COVID and don't even know you had it. What's wrong with that prediction? What's the major issue with it, accuracy-wise?
Sample size?
Yeah. I mean, if I was really silly about it, suppose I only tested 2 people and by sheer bad luck, one of them did have COVID. Wouldn't I come back and say 50% of Bremerton has COVID? And we know that's wrong, but couldn't that happen? If you only ask 2 people, you could just get really unlucky. So if you wanted to test how many people truly in Bremerton had COVID, wouldn't you maybe test 1,000 people, a random sample of 1,000? And that would give you a good answer. So whenever you use data, it's empirical. Now, the one that we like when we can do it is theoretical. So that's what we're going to look at now. Let's do a dice. One of the easiest ones to do theoretical probability on. What's the probability I throw a dice and I get the number 5? Well, on a dice, there's only one number 5, but there are 6 numbers. The answer is 1/6. That is a theoretical probability. You know, I didn't actually physically have a dice here and roll it. All I made was the assumption, which I think is a valid one, that a normal dice has 6 numbers on it, and that only one of those numbers is a 1, and that the dice wasn't weird. It wasn't one of those loaded dice that, you know, bad gamblers make. You know, one of those ones that come up 6s more than they should, right? With those assumptions in place, that is a theoretical probability. What's the probability then that I throw a dice and I get an even number? Well, there's 3 of them, right? 2, 4, and 6, 86. And that simplifies down to a half. So when you do questions in your homework and the answers to be fractions, well, you remember there's an unwritten rule. You always simplify your fractions, right? You never leave them as 3/6. Let's try cards. Now, not everybody knows about cards. Maybe you just don't play them. So here's a little gist of it. Hearts, clubs, diamonds, and finally spades. And there are 13 hearts, 13 clubs, 13 diamonds, and 13 spades. And each one of those are called suits. Each one of those 13 cards are the same for each suit. So you have an ace, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you finish with jack, queen, and king. Right. Here's a theoretical probability. What's the probability I pick one card, right, and it's a king? Well, there are 52 cards in a normal deck, and 4 of them are kings. So that probability would be 1/13. What's the probability that it's a king or a queen? Well, still 52 cards to pick from, and I'm picking one card, but it's a king or a queen. What's the chances that that happens? Agreed. See mouth moving. 8, which I believe simplifies down to 2/13. This one is a trick question. What's the probability that you pick one card and it's a king or a club? And the reason I'm doing this and telling you it's a trick question is sometimes you have to be careful when you count what number goes on the top.
16.
I heard 16. So tell me why you picked 16, because it's a good answer and I like it.
There's 13 clubs and then there's 3 other kings.
Correct. Did you all catch that? Why it's 16 and not 17? Because a lot of people, and it's kind of understandable, would do this. There's 4 kings and there's 13 clubs. So that number up there should be 17. But can you see that there's a double dipping? I call it double dipping. Aren't you counting the king of clubs twice if you do it that way? If you count these together. Do you see why the correct answer is 16? Right. So when you're doing probabilities, especially if there's the or word, will you be just a little bit careful about how you do it? Now, in this question, there are 4 kings and there are 4 queens. And yeah, the top number is 8. What's the difference? Well, there is an overlap here. Isn't there a king of clubs that belongs in both categories? But in here, aren't kings and queens totally separate? And we have a term that we use to kind of compare these things. Try to get my little pen thing organized here. Disjoint and not disjoint. There are other terms, but that's one I like. So if two things are disjoint, they share nothing in common. If they have an overlap, then they are, see if there's anything in the chat. If I get somebody waiting to get in or whatever. No, it's not that. Okay. So you can be disjoint or you can be not disjoint. If they're disjoint, you can just add them all up. But if they aren't, you have to be careful. Let's do another one of these sneaky ones again then. What's the probability that it's a king or it's red?
(28/52), right?
Sounds good to me. 28/52. So for those who are still kind of saying, you know, this is hard to keep track of, here's one way to do it. When you have an or question, how many kings are there? Add to that the number of red cards, and then take away the number that are both, right? So take away, in this case, the number of what, red kings. So let's see where that 28 would come from if you kind of use this formula. Would you agree there's 4 kings? Would you agree there's 26 red, right? 13 hearts, 13 diamonds. And how many red kings are there? Because that's the both. 2. And now you come up with 20/52. Is that the answer you should put into WebAssign? Agreed? What should you, what does that simplify down to?
7/13.
Agreed. And I know it's me maybe being nitpicky here, but the number of people who do the question right and then just make a little, you know, it's so superficial, you just forget about it. And you come and you send me an email and say, I have 5 shots and I don't know why it's plenty, I definitely, as I even got a deck of cards and put them out and counted them and it worked. So how come I'm not right? And it's simply, you just didn't simplify. I mean, it's the simplest mistakes that can bite in the bum, right? You do all the hard stuff and then you fall in the last hurdle. WebAssign is totally unforgiving, isn't it? You know, if it's the right answer, but not the way it should be written or something like that, it'll just say wrong. We're going to look at a concept called sample space that we use in probability. A sample space is a list of all the things that could happen. And very often we have to create this. In other words, we need to write it down. Because to get a probability, don't we need to know the total number of things that could happen, right? How many there are. So the sample space, when you write it down and you add up how many things are in the sample space, that's the guy that goes in the bottom. And then, depends on the question what event A is, you go through your sample space and you count all of these. So I'm going to do a sample space for a family of 3 children. So what I'm going to write down is all the different ways a family of 3 children could be born, right? So boy, 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 girl, boy, girl, boy, and girl, boy, boy. Those three are different events. This one would be your first child was a boy, your second child was a boy, and your third one was a girl. Now, boy with two girls, girl, boy, girl, 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 boy. And there's only one other left, girl, girl, girl. So can you see in this sample space, there are 8 different ways in which 3 children can be born. And although these end up being 2 boys and a girl, and this group here ends up being 2 girls and a boy, do you see that there are 3 different ways in which that can happen? Why is that important? Well, isn't this sample space got 8 things in it? Right? You can't, there's 8. So if I went and said to you, what's the probability that you get 2 girls and a boy? You would say 8 on the bottom, or sorry, 8 goes in the bottom, right? How many of these 8 are a 2 girl and a 1 boy world? Would you agree it's these 3? And that is the answer as a fraction. And I'm just going to turn it into a percentage. And that's about 37.5% of the time. Now, let's pretend that we didn't have a good grasp of probability. We had a kind of half good grasp, but not a perfect grasp. You might do this and it would be wrong. I know how you do this for a family of 3 children. You write down all the things that could happen. So you say, there's 3 boys that could happen. There's 2 boys and a girl that could happen. There's 1 boy and 2 girls that could happen. And then there's 3 girls that could happen. And you say, there's 4 things that could happen. And only one of them is 2 girls and a boy. And you come up with 25%. Can you see that the logic might seem sort of a correct, but doesn't it not give you the correct answer? And the reasoning behind that is that 2 boys and a girl isn't really the best way of doing that. Don't you really need to write down all the different ways in which that could happen? And a lot of people don't when they do that. And that's why, although it's a bit laborious, would you agree you kind of need to do this? Now, once I've got this sample space, I can ask all sorts of questions. For instance, what's the probability that your first child is a boy and your third child is a girl? Right, 8 goes in the bottom. The first child is a boy and the third child is a girl. Don't you search through these 8 and see which ones that qualifies for, right? So the first child is a boy and the last child is the third child is a girl. So that one counts, would you agree? None of those 2 work. First one is a boy, last one is a girl. Would you agree that one works? Is there any more, or have I found them all? Found them all? So the answer to that would be a quarter. Couldn't I find the probability that the last child's a girl? Probability that you had more boys than girls? Probability you didn't have any girls? Right? You could answer any kind of combination you like, as long as you've got the sample space. Isn't it just a matter of counting which ones of the 8 fit the story? Any questions so far? Okay. At least we're getting to deal with numbers again, right? Things that have answers that you don't need to argue about, right? Well, hopefully you would agree with me that that's the right answer and this is the wrong one, right? Hopefully you would agree with that. So I'm now going to go a little bit esoteric. That's probably a better word. It's called the Monte Carlo fallacy. Fallacy means it's a falsehood, it's wrong, right? And the Monte Carlo fallacy is to do with probability. I'll give you a version of it. You might or might not know this, but Monte Carlo is a famous place in, I believe it's in, well, it's a country of its own, but it's right in the south of France. And one of the games they play a lot there is roulette. If you've ever watched James Bond, right, he's probably played roulette at least in every movie he plays, right? You roll the ball and it stops on a number. What happens in this game is that you bet a number or a colour, and if you win, you get money, and if you lose, they take money off you. And the Monte Carlo fallacy goes something like this. Imagine that you've rolled this ball 10 times, and every single time it was red. People look at the probability in the wrong way. And there are two versions of it. Version number one. Wait a minute, the chances of you getting a red are almost a half, right? Half the time it's red, half the time it's black. I mean, it's not quite because there's a green there, but roughly, right? Half the time it's red, half the time it's black. There are tons of red. Reds are hot. I'm betting a red. The other people say, wait a minute, things should be balanced here. If you get a lot of reds, shouldn't you get some more blacks to balance it, right? It's got to be 50-50. So I'm going to bet that the next time it's going to be a black. Okay, the ball's on the roulette wheel. I'm giving it a spin. What's the chances that it's going to be a red? Is it any better than it was, you know, when they opened the door in the morning? Doesn't the probability stay exactly the same? Probabilities do not care what has happened in the past. Right? If you throw a coin in the air and just by sheer luck, you get 10 heads in a row, see the next time you throw that coin, isn't it just 50-50? Could be a head, could be a tail. Isn't it still 50% heads, 50% tails? The fact that the first 10 times you threw it were all heads has no effect on the future, right? And the Monte Carlo fallacy is people think it does. They think if something has happened in the past, somehow that's going to affect future probabilities of things that are random, like throwing coins in the air. Well, let's take it to its silly extreme. Let's do the coin one. I've thrown the coin 10 times and it's heads. I'm about to throw it for the 11th time. If that coin had, if the probabilities changed, wouldn't that coin have to have a memory? Hey, I've just been heads 10 times. I better get a couple of tails in here to average it out. So when you throw in the air, the coin decides to wiggle itself to become a tail. I mean, that's silly. Would you agree? It's an inanimate object. It doesn't know what's happened to it in the past. Probability is not used to tell you what's guaranteed. It's used to give a number for how likely the next time it's going to be whatever it is you're looking for. And that is called the Monte Carlo fallacy. And a lot of gamblers lose a lot of money based on using that principle, that somehow what's happened in the past is going to affect their chances of winning in the future. Here's a totally different version. Do you know if you win the lottery? I hope you do. Do you know if you buy a lottery ticket next week, isn't your chance of winning the lottery exactly the same as it was any other day that you buy a lottery? Right. If you win, you win. It doesn't change that you won last week. It's the same game, same chance. Are we good? Right. Time for one last sample space. Okay. I don't know if you've ever seen one of these things, but do you know that you can get dice that look like little pyramids? And when you roll these dice, the number you get is actually the number that's on the floor. So you roll the dice and you pick up and say that was a 2, and then you roll it again, you pick it up and you said it's a 1. There are only 4 faces to this dice, so it's the numbers 1 to 4. And imagine I've got 2 of them, right? This one is green in color, and this one here is red in color. So I kind of color coded them. And you've got 2 of them, right? You've got a red one and a green one. You give them a good shuffle and you roll them. We're now going to write down what the sample space for this event would be. And the way I'm going to write it is as if it was coordinates, but it's just a way of writing down the information. See, this would be, both of them are 1, right? This one would be, green one is a 1, red one is a 2. Right. I'm not going to do the rest in, well, maybe I will. If you count the boxes, can you see that there's going to be 16 things in the sample space? Agreed? So here goes. Try and be as quick as I can. It's going to have to be our last question for today. Are we comfortable about why that sample space is what it is? Can you see that there's actually, what's that, 16 things it could have? So here's the first probability that we're going to use this sample space for. What's the probability that I roll these 2 tetrahedron dice and they add up to 3? Well, the bottom number is kind of fixed, 16. What's the top one going to be? How many ways can you get a total of 3 in this situation, this world? Agreed? 2. Which will simplify in 8. What's the probability that you get an even total? Well, let me speed this up for you. An even total would be that guy, because that adds up to 2, agreed? Doesn't that add up to 4? This one adds up to 4, and this one adds up to 4. So wouldn't that count as even? Great. This one adds up to 6, this one adds up to 6, and this one adds up to 6. So that counts as even. And won't this one here add up to 8? So what does that give me? 1, 2, 3, 4, 5, 6, 7, 8. And that is half the time. My last question. Which total is the most likely? In other words, which total would have the biggest probability? Any takers for that one? What total is the most likely total if you roll 2 dice in this story? Agreed.
5.
So some, yeah, 5. Does that surprise you that it's a 5? Let's check it. There's 1, 2, 3, 4 ways in which you can get a 5, right? There's 4 of them. Now, what a lot of people do who don't do sample spaces, if I ask them the same question, their logic might come out something like this. Well, that's a number 1 to 4, and that guy's a 1 to 4. So the middle's a 2, the middle's a 2. So I think it'd be a 4, you know, that kind of thing. I mean, the logic is flawed, but that's what they would do. When you see the sample space, do you see sometimes you might get answers that are not what you assumed?